Good morning, almost afternoon, everyone. Thank you for coming today. My name is Brandy Carrier, and I'm going to be presenting some of the advanced planning and planning considerations related to searching for biosignatures in the samples that we're hoping to return via Mars sample return. I'm presenting this on behalf of some of the MSR campaign science leadership, including Michael Meyer, Gerhard Kaminik, Minnie Wadwa, who's here in the front row, Dave Beatty, Fiona Thiessen, and Lindsay Hayes, but I'm going to be handling the presentation today. So just a little bit of an overview of the Mars sample return campaign. Can you guys, everyone can see the slides? Okay. So as I'm sure you all know, the Mars sample return campaign is broken into several different kind of components. The first component, of course, is the Mars 2020 sample collecting rover, which is doing fantastic work right now on Mars in Jezero Crater, which to establish the geology of the samples, to do the sample selection and acquisition, documenting the sample context, and using all their in situ instruments to generate some advanced knowledge of the samples to be returned. And then the Mars sample return consists of the flight missions, which will go to Mars and retrieve the samples and return them to Earth, hopefully returning the samples in 2033. So it's a very complex series of missions. There's, of course, going to be a sample retrieval aspect for which the architecture is kind of still in flux. But the samples, some of the samples may be delivered by the Mars 2020 rover directly to the sample retrieval lander, and then the samples will be launched off Mars via a Mars ascent vehicle and released into orbit, where they'll be intercepted by an Earth return orbiter, which has a capture, containment, and return system, which essentially seals the samples inside two layers of containment, which essentially breaks the chain of the contact with uncontained Mars material to protect the Earth's biosphere. And then the ERO will transit back to Earth and release an Earth entry system into Earth, and then hopefully land somewhere in the Utah desert, as I mentioned, in 2033. Now, from a sample science standpoint, one of the most important things in these flight missions is to maintain the integrity of the samples throughout all of these phases, including things like not subjecting them to environmental extremes that would compromise our ability to do all the science we hope to do when the samples come back. So today I'm actually going to focus mostly on what happens after the samples come back. So right now we're in kind of a pre-formulation phase for a sample receiving project, which will be all of the Earth-based infrastructure for the MSR campaign, including a sample receiving facility where the samples would be held under BSL-4 containment until they're either deemed safe for release or sterilized. So of course we'll have to do a sample safety assessment, a lot of curation-based activities like basic characterization and preliminary examination of the samples, and then a lot of, hopefully, competed sample science investigations, both inside and outside the sample receiving facility, to kind of get all the science answers we're hoping to get with these samples. So because this is an astrobiology conference, I'm going to focus on kind of the planning considerations that we're thinking about that we need to do to optimize the sample analyses related to looking for biosignatures of extinct or extant life in the MSR samples. And so there's five main topics I'm gonna mention here. The first being contamination control and knowledge for the samples, which of course is going to be very important to distinguish between an actual Mars biosignature and potential terrestrial contamination. As I mentioned a moment ago, avoiding environmental extremes that could alter or degrade potential biosignatures. So things like avoiding elevated temperatures and avoiding high impact scenarios that could potentially pulverize the samples and impede our ability to look at stratigraphic context and molecular patterns in the samples. And then the measurements and investigations that will be needed to complete the sample safety assessment. And then, of course, also any other measurements of potential biosignatures, determining whether they could be performed on sterilized samples outside biocontainment or whether they need to be planned for as part of the initial set of experiments inside the biocontainment facility. And then another really complicated topic is kind of planning for the sample investigation workflow that can accommodate the measurements I already mentioned, as well as measurements that are time sensitive. So I'll touch on each of these things a little bit in the presentation and then open the floor for any comments or questions on this topic. So For contamination control and knowledge, the Mars 2020 rover had very stringent requirements on contamination, as well as a comprehensive contamination knowledge program. The overall goal is for the returned samples to basically have less than 10 ppb of total organic carbon in each sample tube. That represents terrestrial contamination. And there were actually more stringent limits of, I believe, 1 ppb for several compounds that are designated tier 1 compounds, which are compounds that are likely to be indicative of past or present life. So very, very strict requirements. And then the flight missions, which are currently under development, are also following a strict contamination control and knowledge plan to limit any organic contamination that can enter a sealed sample tube while the samples are in the custody of the flight missions. Because as everyone in this room knows, that contamination can really impede our abilities to make definitive measurements and conclusions when we do our scientific analyses. For the sample receiving project, we are currently working on developing those contamination control and knowledge requirements and an implementation plan for achieving those. So one of the really complicated things about this sample receiving facility is not only does it need to be a BSL-4 containment facility to prevent anything from getting out and potentially contaminating Earth's biosphere, but unlike traditional BSL-4 facilities, we also have to worry about contamination getting into the samples. So there are a lot of potential implementations that could mitigate that, things like double-walled isolators where you have a positive flow and a negative flow, both protecting the samples and the external environment. So that is an activity that is ongoing, and we plan to kind of come up with a draft implementation plan for that in the next couple of years. Okay, so for sample environmental control, biosignature degradation will occur if the MSR samples are exposed to temperatures that are significantly higher than they've seen in their natural history on Mars. And I believe Mark Sefton has a presentation on this tomorrow. We had formed a temperature time tiger team earlier this year, and their final report is about to come out very soon, that looked at what are the consequences to the science we can do with the Mars samples if the temperatures are exposed to temperatures above 30 degrees C for varying periods of time, and what are the implications of that for science. And that information is used to evaluate any requests or waivers from the projects to exceed that plus 30 C temperature. So right now we have a maximum temperature requirement of plus 30 C during the retrieval and transport of the samples to Earth. And we're very much hoping that we can meet that requirement. We also have reason to believe that the samples will not have seen temperatures higher than that during the custody of Mars 2020, or potentially while sitting in a depot on the Martian surface. And again, for the sample receiving project, it's a little bit easier to do thermal control in a building than it is on a flight mission. So we expect there to be similar thermal requirements for the MSR samples, and including the ability to potentially preserve select samples or sample splits at much colder temperatures if we think there are signs of labile biosignatures of extant life or extinct life. The other environmental consideration is impact and vibration. As I mentioned, a lot of the value of these samples comes from having sample cores, where you can see the stratigraphic relationships of different minerals and different depositional layers to each other to kind of derive a history of habitability and potentially a history of biosignatures on Mars as the samples were naturally deposited. So there is a general goal for Mars sample return as a whole, including Mars 2020 and the flight missions, to limit the overall fracturing of the samples so that greater than 65% of the samples are in pieces with the longest dimension no shorter than 10 millimeters. So that even if we do have fracturing, we can hopefully reconstruct, well, it's like a puzzle, right? Putting the puzzle pieces back together. But obviously the less fracturing we induce, the better. And currently there's an activity underway by the Mars Sample Return Program looking at all their different vibrational and impact environments throughout the entire course of the retrieval and delivery missions to ensure that we can preserve those samples. So once the samples arrive at the sample receiving facility and we start, extracting them from the hardware and hopefully opening the tubes, there'll be a suite of curation activities. For example, CT scanning of the tubes before they're opened and things like that to get an idea of the context and how the pieces of the samples fit together and to identify the samples to potentially open first. So as I mentioned, due to planetary protection concerns, all of the samples will have to stay under biosafety level 4 containment until they are deemed safe for release via a sample safety assessment or until they are sterilized. Now, two of the most common ways to sterilize samples are with high heat or with radiation. And both of those things would impact the preservation of biosignatures, particularly organic biosignatures that we really want to look for in the samples. So how do we actually prove that the samples are safe? I'm sure, as you can imagine, this is a complicated question because essentially you have to disprove life rather than prove life, and it's very hard to prove a negative, as I'm sure you all know. So over the last few years, the Committee on Space Research, or COSPAR, the Sample Safety Assessment Framework Group, has been working to kind of develop a framework for how to go about implementing a sample safety assessment for the MSR samples. So the objective of the safety assessment would be to evaluate whether the samples returned from Mars could be harmful for Earth's systems, for the environment, for the biosphere, for geochemical cycles. And so the scope of the sample safety assessment framework was to evaluate whether the presence of Martian life can be definitively excluded in samples from Mars to within a certain confidence ratio. If the presence of Martian life can't be excluded via a series of investigations, a hold and critical review phase would be established to evaluate the risk management measures and decide on the next steps. So there's actually a paper put out by this working group that's going to be available online in Astrobiology in the next week or so. So you'll be able to look at more details at that point, but I'll just go through a little bit of the report here. So there's a few principles that provide the basis of this framework. So first of all, the use of a hypothesis-driven approach in the development for life detection investigations. So the measurements for science, which basically starts from the null hypothesis that there is no life in the samples, and the sample safety assessment, which starts from the positive hypothesis and attempts to disprove that there's life in the samples. Although these are two different regimes, it relies on a lot of the same types of measurements and scientific investigations as we go forward. So the sample safety assessment has to be data-driven, and it needs to be responsive to the results of different investigations as the results are derived. So the main distinction between the scientific objective to search for life and the sample safety assessment is mainly the degree of rigor and supervision that will be applied. So there'll be a much higher standard for evaluating whether the samples are actually safe than potentially there is in looking at science results for science sake. And a lot of regulatory agencies will be involved here, for example, the CDC and potentially the EPA and other governmental regulators. So there's a few major elements that drive the sample safety assessment framework. The use of Bayesian statistics, so you start with a starting hypothesis of what is the likelihood of there being life in the samples, estimating the number of tests you will need for each sample tube, how many subsamples you'll have to analyze, and then a targeted subsampling strategy, which would be used to identify the pieces in the samples that have the highest priority for preserving evidence of extant life, which is really the question here, although a lot of the investigations that you would do for extant life are similar to the ones you would do for extinct life. And so this requires structural, chemical, and mineralogical information to be collected during the test sequence. And then there'll be a need to set up a decision framework, which will include regulations for quality control, what are the processes for data reduction, what are the criteria for the various steps in the test sequence, and then when do you pause and review if you have a positive detection or an uncertain detection. So the main purpose, as I mentioned, of the test sequence is to exclude the presence of Martian life, specifically extant Martian life. So the sensitivity and specificity of the overall test sequence in each experiment that's done in the test sequence influences the number of tests needed to achieve a certain level of assurance. So, and then once you've done all these tests on N subsamples of a specific sample tube, you have a result that you think is verified within a predefined level of assurance. It's only valid for that one sample tube because, as we know, the samples are collected from different places and they're representative of different periods in Martian time and different environments, which may or may not be more conducive to extant life. but the results you get from one sample tube do inform the pre-test probability for other sample tubes. So here's kind of an overview of the integrated test sequence that's being proposed by the Sample Safety Assessment Working Group. So you can see that there are basically 9 steps here. It includes things like the 3-dimensional structure of the samples, analysis of the headspace gas from the sample tubes, looking at the chemistry and mineralogy of the samples, and then using refined subsampling to choose the subsamples that have the highest probability of preserving extant life based on the chemistry and mineralogy. And then a suite of analyses related to looking for organic molecules, molecular patterns, macromolecules, and these steps 4 through 6 all kind of feed into step 7, which is to exclude life as we know it from the samples. And then, of course, there needs to be another step, which is step 8, which uses other more agnostic life detection measurements to rule out life as we don't know it. And then, again, a stop and a critical review phase to determine whether we have actually excluded Martian life in the samples to a defined degree of assurance. And then you can decide on the next steps. Is that sample that was in that sample tube, is it safe to release to outside laboratories for further analysis? Are more analyses needed? Does the sample indicate that there is Martian life in the sample tube, in which case, of course, there's a whole other suite of experiments you want to do, but you'd have to do them inside biocontainment. You probably wouldn't want to sterilize a sample that you think has Martian life in it until you've fully analyzed anything that's in that tube. So again, these point to more things that would need to be done in a biocontainment environment. Whereas if you think you've definitively ruled out life, perhaps you could release that sample for all kinds of other measurements outside containment. So in order to fully kind of scope what needs to be done in a sample receiving facility, we need to think about all the possibilities. If we can't rule out extant life in a sample tube, and we can only release samples that have been sterilized, and we need to know what kind of measurements and investigations would be impacted by those sterilization processes. So the MSR Science Planning Group 2 has a report on this topic trying to identify all of the potential objectives of Mars sample return, all of the potential investigations we'd want to do, starting from the International MSR Objectives and Samples Team study from 2018, and deriving which of these investigations would be degraded or altered if we were to sterilize the samples using either thermal or gamma irradiation sterilization techniques. And again, this report also is available. This one's already available online in Astrobiology today. So the challenge, as I mentioned, is that the samples are going to be held in biocontainment until they're deemed safe or are rendered safe via sterilization. And we know that sterilization processes would permanently alter certain characteristics of the sample. And a lot of those characteristics are things that have high value or high interest to science. So if these measurements aren't planned to happen inside the sample receiving facility, scientific information may be lost. So the starting point here was to identify the sample attributes that would be vulnerable to alteration via either heat or gamma irradiation sterilization. And of course, this includes biosignatures of extant or extinct Martian life, potentially the composition of the sample headspace gas, which has evolved from the sample during transport, indicators of paleohabitability and biosignature preservation potential, and also properties of either volatile rich or amorphous materials, which are very sensitive to elevated heat. And then we also identified overlap between measurements that are time sensitive, which I'll talk more about in the next module, and then sterilization sensitive. And then we feel that we can plan to conduct anything that's quote unquote sterilization tolerant outside of the sample receiving facility. So there are many measurements that aren't related to organics or biosignatures, things like geochronology related measurements, things that are much more tolerant to high heat. So theoretically, some samples or subsamples could be sterilized relatively quickly and released to outside laboratories to do these types of investigations. So we didn't worry too much about those because we think that there's a good pathway to get those done. And so one of the main findings here was that most aspects of MSR science should be planned to be performed on samples deemed safe in uncontained laboratories, so whether that's by sterilization or the sample safety assessment. However, other aspects of MSR science would be both time sensitive and sterilization sensitive, including and especially the search for life, assessment of habitability, and volatile exchange processes. So these we need to plan for how to carry them out successfully inside a biocontainment facility. So one of the kind of key strategies here, you see this this red box that says SRF. These are the things we think need to happen within the sample receiving facility. We need to have the instruments and the capabilities and the infrastructure to do these. So there's the curation related things that I mentioned. So basically everything you need to do to develop a sample catalog and effectively allocate the right samples for the right investigations. The sample safety assessment protocol. Any science that's time sensitive, so basically things that start to change or re-equilibrate once you remove the caps from the tubes. And then any sterilization sensitive science that overlaps with those above three categories. And then you have this decision point that you reach after the sample safety assessment. Is it okay to release unsterilized samples? If yes, then you release the samples and you work on released unsterilized samples in uncontained labs, all over the world. If it's determined that we can't release unsterilized samples due to, a positive or inconclusive result, we could sterilize and release some samples to uncontained laboratories for things that are not sterilization sensitive, but we would need to add contingency capability inside biocontainment somehow to do any other sterilization sensitive science. And particularly if signs of life are detected in the samples, you can imagine a whole suite of experiments you would want to do to characterize that life. And that would have to be done under biocontainment conditions, one way or the other. So this goes back to, again, how do you develop a sample workflow that makes sense, that accommodates all of the measurements that I mentioned, plus the time-sensitive measurements? So, as I just mentioned, as I mentioned several times, the samples will be held in the SRF until they're deemed safe. But once you break the sample tube seal, you're going to get an equilibrium change that's going to cause irreversible changes over time, particularly in volatile-rich samples, where you have an equilibrium between the Martian atmosphere that's been in the sample tube for however many years since the samples have been collected until the sample tube is open. And then you'll potentially put that open sample tube under, an inert atmosphere, which tend to be pretty dry. So you're going to drive dehydration reactions, among other things. So this group of the MSR Science Planning Group Phase 2, which also has a full report available on the Astrobiology website, tried to identify what processes would contribute to degradation of important sample attributes at the timescales of several months or less, which we estimate is the amount of time it would actually take to deem a sample safe and send it to do analysis elsewhere. And they identified things like degradation of organics, which of course is a key driver for the astrobiological investigations, modification of the headspace gas, and mineral volatile exchange. So we want to ensure that the sample receiving facility is capable of performing these measurements required to investigate those kind of attributes before they've been altered to the point where we lose valuable science. So this working group tried to define the time scales of the processes that would underpin these time sensitivity measurements. And we know that we need to move quickly for some of these once the sample tubes are open. So you can see that there's kind of four main categories here, which is the degradation of organic material, which can happen on the order of hours or days, particularly if there's H2O or reactive oxygen species present in the samples. And then the change in the sample headspace gas composition, which is, kind of dependent on how well we're able to capture that gas when we're opening the tube, among other things. But then there's volatiles that are bound to the samples. So things that are like hydrated sulfates or perchlorates or clays can start to lose adsorbed water or bound water, again, on the time scale of hours to days. And the same thing with the hosts of these kind of solid phase volatiles. And so everything you kind of see here under the hours to days categories are things we think we need to have the instrumentation to do those things inside the sample receiving facility. So I've mentioned there's a lot of things that need to happen in the sample receiving facility. So it's really complicated to kind of optimize that sample workflow and to identify what are the key objectives for the sample receiving facility. So this is kind of a summary of the things that we've identified. So of course we need to be able to receive the return spacecraft and carefully take it apart layer by layer while preserving the integrity of the samples. Provide an environment consisting of BSL-4 containment and a very high level of cleanliness and contamination control, as well as physical security. You can imagine these samples are going to be very, very valuable. We need to put all the samples into a safe and stable state, including the gas from inside the tubes, any dust that's on the outside of the tubes, and allow curation to complete the initial characterization of the sample so that the right pieces can be allocated for the right investigations. And then enable all the specific science investigations that I mentioned previously, including those needed for the sample safety assessment, which is really key. And then enable sample allocation and pristine sample storage. And then supporting the transition to post-SRF activities. So we imagine that the sample receiving project will have a set of objectives, the primary science objectives of MSR, and those will be part of the project. But as we know from looking at previous sample return missions, there will be samples and we'll be working on them for decades to come. But once there's a definitive endpoint for the project and the primary science objectives are achieved, we'll kind of transition into a phase where hopefully all the samples have been deemed safe and they move to uncontained curation facilities, and it would go through a kind of the same kind of allocation and ongoing RNA as we have for the lunar samples, for example. So this is kind of our concept of operations, which kind of summarizes what I just said here. You see the return spacecraft arrives. We have all of the sample dossiers and all of the data collected from Mars 2020. And everything in the red box is what happens inside this biocontainment barrier, including the spacecraft receiving and deintegration. We extract the sample tubes from the flight hardware. We wipe all the dust off the sample tubes because we're going to want to do science on that too. We do the pre-basic characterization, so any measurements we can do through a sample tube, for example, CT scanning, potential bulk magnetic measurements. And then we need to move these samples into basically pristine isolators with super high levels of contamination control, where we can extract the head gas from the tubes, open the tubes, allow the basic characterization to be complete. And then you can see that the arrow pointing down from that green box is for unsterilized subsamples. So there's preliminary examination, there's the sample safety assessment, the sterilization science, and the time-sensitive science. And we envision that all of the science measurements that take place, there will be competed science investigations done by people like yourselves who write proposals to be on this kind of sample receiving project science team and be the first people to do these measurements. So that's how we envision that happening. And of course, all of these results go into evolving sample catalog that includes scientific publications, all of the safety reports, et cetera. And then hopefully we can move to laboratories outside of containment. And again, all of this, we hope, comes to the realization of everything that we've all hoped that we'd be able to achieve with samples from Mars at the end of this. So again, this is an eye chart. Don't try to read this. There's been some thinking about how do you optimize a workflow inside a sample receiving facility. This is derived from the MSR Operational Scenarios Definition Team, whose report I believe is available on the MEPAG website, but I'll have to double check that when I get home. This is just kind of a draft of where do you start and where do you go and how do you open all these layers and what kind of environments do you have to do each step in and what happens in a double-walled isolator, what potentially happens in a BSL-4 suit lab, what measurements can be done through a port in an isolation chamber versus need to be done out on a bench. And optimizing all of that is very much a work in progress. And this is the reason we really need to start this planning early. We need to know what this sample receiving facility capabilities are going to be and how do we optimize it to make sure we get the best science out of this. So looking ahead, a lot of this is derived from the MSR Science Planning Group 2 reports and work that has happened subsequent to that. So the first thing is to initiate, a comprehensive MSR science program. So NASA and ESA are very much collaborating on this. So currently they're working on finalizing the documented and signed agreements between NASA and ESA to define the end-to-end science program, including a science memorandum of understanding, an MSR joint science management plan, and importantly, to seek the necessary funding and authority to implement them. So this plan is expected to be finalized in the next couple months. And then in addition to that, one of the recommendations of MSPG2 was to establish an MSR campaign Science Group, which is a group of international scientists who can advise on all of the issues that I talked about previously, planning for the sample receiving facility, making sure we have the right requirements in terms of contamination control, making sure we know what the specifications of the instruments that we need to, put out proposals for the SRF need to be, potentially run a science definition team, do a science traceability matrix once we really know what the samples are we expect to be returned. So the call for applications for the first phase of that group, which will be recomputed every 2 years, was issued, I want to say April, and we actually expect the selections for that to be announced in the next week or two. So that's probably a group of around 15 to 20 external and scientists with some ex officio members who are kind of an advisory group to the MSR projects to make sure that the science community is being represented and that the science is being protected. And as I mentioned, the next phase in MSR after the flight missions is this sample receiving project, which is kind of currently in an informal pre-phase A state. So we need to formalize the organizational structure and funding for that process, which will be led by Johnson Space Center on behalf of ESA and NASA's Mars Exploration Program. This project is expected to proceed to phase A in FY23. So we are working to get that underway. Additionally, we really need to make sure that we have funding for research and development and R&A activities to plan for the analysis of these MSR samples. So we need to utilize or augment existing funding mechanisms or find new mechanisms to support, short and medium-term studies required to carry out the MSR science program. So this would include things like, an analog program to kind of determine what are acceptable sterilization techniques for a geological sample rather than just a surface, because that's something that still needs more study. Making sure that any proposed sterilization technique goes through all of the reviews and processes it needs to be accepted by the regulatory agencies. Optimizing what kind of measurements can minimize the use of sample mass. I mean, we have a very limited amount of sample being returned from Mars, and we want to make sure we make the most of it. So there's a lot of kind of optimization experiments that need to be done, in addition to technical development for things like isolation chambers that provide BSL-4 containment, but that can be moved from instrument to instrument, and potentially even to, instruments outside of a BSL-4 facility, and making sure that those are at a technology readiness level that's acceptable to regulatory agencies for PP reasons. And then, of course, to continue to refine the requirements for the SRF, for the sample receiving facility, for the environmental conditions, the cleanliness, and to translate this into a curation plan, the overall concept for the facility, budget, and schedule. The idea, hopefully, is that we would start having a site-specific design for the sample receiving facility in FY25 to be able to start construction and get this done before the samples arrive. So, as I mentioned, some of the, the ongoing activities that are coming up soon, again, the finalization of the science management plan. This will, include content related to the science and sample management structure, including identifying all the ways that the science community can be involved in the planning and implementation of MSR science. Because this is the whole point. This is why we're doing MSR, is to do this science when the samples come back. Again, how the science data is going to be handled, what are going to be the publication and communication policies. And so this is based on kind of 5 guiding principles, which include, scientific maximization, accessibility to the international science community, transparency, the principle that although the samples may be in different locations at different times, including in the long term, some may be in an ESA curation facility and some may be in a NASA curation facility, but this really needs to be managed as one collection. So if someone is, proposing to do an analysis of an MSR sample, we're really looking at the whole collection to find the best piece for that specific analysis. And then, of course, return on investment for the partners who are making the investment and actually bringing these samples back from Mars. I already mentioned the campaign science group. So this group is going to be co-chaired by the NASA and ESA MSR lead scientists. Those positions currently being held by Michael Meyer for NASA and by Gerhard Kaminik for ESA. And so this group, again, will assist these lead scientists in the execution of the science management plan to really ensure that we're maximizing the science potential of MSR by establishing the processes for decision-making and establishing and maintaining the process whereby the science community is involved in return sample science. And again, this group will function in an advisory capacity. We actually received about 80 applications from the international science community. And as I mentioned, these selections are expected by June 2022, but hopefully in the next week or so. Again, I mentioned that the sample receiving project would be managed by Johnson Space Center in coordination with ESA and with NASA's Mars Exploration Program. So the sample receiving project, again, is meant to encompass all of the non-flight aspects of the campaign, beginning once the samples have touched down on Earth and ending when the primary science objectives are met. So there are draft objectives that I've written here for this project, not finalized until we, move into a pre-project review. A lot of it is very similar to the objectives for the facility, except that we need to, conduct these science investigations inside and outside the SRF and make sure that there's funding and that this project won't end until those science objectives are met, and then to provide and enable long-term curation. And I think that's the end. So I'm happy to take any questions or comments from all of you. Thank you. Can we turn those on?
Hello? Can you hear me?
Yeah.
Hi, Brandy. Navita Naz, Tufts University, Massachusetts. I just want to say that was really, really interesting.
Thank you.
I had one quick question.
Mm-hmm.
So when you talked about sterilization of samples, have you thought about you already know, but the presence of perchlorate in those samples, would they not destroy the things you're looking for?
Yeah, so that was one of the factors that was taken into account in terms of looking at what's sterilization sensitive. I mean, you said you're from Tufts University?
I'm going to come talk to you after.
Sorry, that's also where I went to grad school and looking at perchlorate in the samples. So in the Phoenix samples. So yeah, so that's certainly something that was taken into account in looking at what's sterilization sensitive, and also in terms of looking at what is sensitive to elevated temperatures over time is the presence of not only perchlorates, but other oxychlorines that may be reactive, as well as, things like OH radicals, superoxides, because of course those things kind of reduce the temperature at which you're, worried about the temperature and time at which you're worried about degradation. So yeah, that was definitely taken into account.
Okay, thank you.
Hi, Brandy.
Hey, Ellie.
I'm actually wondering, when you're doing your safety assessment of the sample, how much sample processing can you actually do during that process? For example, are we allowed to flatten the surface for a non-destructive spectroscopy technique, or does it have to remain completely intact and we can't do things like take a slice or things like that? Because it seems like I'm thinking through various techniques, and it seems hard to do that on a non.
Yeah,
and surface or things like that.
It's hard to see in this thing here, but I will refer you to this paper, which, like I said, will hopefully be out in the next week or so. But a lot of the identified measurements and analyses are on process samples, whether it be a powdered sample of which you've done bulk organic extraction, or the ability to do thin sections or thick sections. So those are other, I maybe should have had a couple slides about the kind of curation and sample processing needs inside the SRF, because some things need a flat surface.
But that's okay during the safety protocol. You can imagine sometimes you powder a rock, you're like, I don't want to bring that in if it's full.
Yeah, so again, this goes into how do you safely do that? Does everything, can you do rock polishing inside an isolator and then put it through a port into a small container? Those are, again, but this is why we need to optimize that workflow. But we do anticipate being able to do a kind of complex sample processing even during the sample safety assessment.
Cool, thank you.
Thanks.
Hi, I'm Carlos Cruz-Arce from NASA Goddard. I was wondering, for the ride back home from Mars to Earth, will the radiation on the ride back home affect the samples at all?
You're standing next to a very appropriate person. Um, no, so the kind of radiation environment that's expected during the transit is actually kind of a very small dosage of radiation compared to what the samples will have already seen on the Martian surface over, millions of years.
Thank you.
Hi, Chad Pazariski from Georgia Tech. So I'm wondering about what sort of technology development is required for manipulation once it gets back on the ground. And I imagine there'll be, when it comes to uncasing the device, that'll be specific technologies that will be designed when the device itself is. But also for manipulation of the samples at small scales and for the requirements that I guess are very unique to these samples. So are there any plans for funding technology development opportunities specifically for that?
Yes, there are. So this is something that, Johnson Space Center has been working into their, long-term kind of technology R&D program for the SRF is, what can be done potentially remotely with micro-manipulators. And even for opening the spacecraft, we started talking about, well, what if you needed to take apart the hardware inside an isolator robotically? And so there's, been a drive to simplify that process. There's a lot of pieces which we can take apart with a screwdriver, which, that kind of thing is easy. But then, of course, there's, things that are hermetically sealed and need a little bit more doing. And then how do you do that without introducing contamination if you have, lubricated motors or, micro-manipulators? So that is a long-term, technology development thing that needs to be done. And then to optimize, the cost-benefit analysis of doing things remotely versus having everyone in a suit all the time. So yeah, that is a long-term thing, and I do anticipate there being opportunities to do those kind of tech development projects and to optimize that kind of thing. Yeah.
Just briefly, have any objectives for timelines for that been set?
No. Stay tuned.
Okay.
Like I said, we're working on getting this, this campaign science group together, and we anticipate that group is going to suggest a technology, an R&D roadmap, and to try to prioritize which things need to be known earlier versus later, and how best to allocate funding for those things, so that if there are things like you mentioned that are kind of needed to plan, how to design a sample receiving facility, those may need to be done earlier versus some of the analog experiments, but it's still very much kind of TBD.
Okay, thank you very much.
Yeah.
Hey, Brandy, Aaron Regberg with NASA Johnson. I wonder if you could talk a little bit about what NASA needs from the scientific community in terms of science communication about this mission, so that we avoid, fears about Mars COVID or Andromeda strain style. Like, I mean, I think everybody in here is excited about bringing Mars samples back, but there are people that are going to be worried about this.
Yeah, so that's a really good point. So I think that, I think that the key is, if you're asked a question about MSR, and particularly in terms of, biosafety, I think the idea is that we do not expect there to be extant life in the near surface of Mars for many reasons, which most of you in this room are probably familiar with. This is basically being done out of an abundance of caution, and to really ensure, because we have to go by, the COSPAR planetary protection policies, to really make sure that there is no chance that we're going to contaminate Earth's biosphere. And I think that's the key point. And potentially, attending, NEPA public hearings, and, if you're asked for a statement on MSR, make sure that, yes, I'm going to be careful what I say here. Sorry, Aaron. No, but, wouldn't it be cool if there was life in the samples? But, I mean, I think we all think that that's really, really highly unlikely, and this is really a risk mitigation and public perception problem more than anything else. Yeah. Oh, sure.
Actually, I was just going to address the previous question.
Yeah, please
really
do.
Quickly as well. Minnewadra, Arizona State. That's an important point that Brandy just brought up, that, I think the likelihood of finding extant life, we believe is going to be very, very low. The other thing to also point out is that we have been, Earth has been impacted by Martian materials over geologic time for we've got a lot of that material around, and many of those rocks presumably came from deeper portions of Mars than what we're going to be sampling on the surface. And, that's not been a catastrophic event for Earth. And so I think that that's another important point to communicate as and when you're able to do that.
Yeah, that's a key point that, none of the Martian meteorites that we know have impacted Earth have caused any problems. I can't see online questions. Do you want to read that or? Sure. Okay. Yeah, Dave, that's certainly the intent, that we would want to capture the gas behind any kind of inequality, seal, which may include the secondary containment vessel and the primary containment vessel. We expect that the orbiting sample container itself is vented, but there may be gas we can capture from behind the primary containment vessel, which will be sealed, in Mars orbit. But we think the highest, amount of gas we're going to get is from inside the sample tubes. So that includes both the headspace gas and, atmospheric sample tubes, or basically sample tubes that Mars 2020 has sealed while empty to kind of deliver atmospheric samples. Yeah.
Hi, Annalise Meyer, MIT Woods Hole Oceanographic. I was wondering, should samples be deemed unsafe to release and sterilization sensitive science? Should labs looking to perform sterilization sensitive science count on being able to work within the SRF, or is that going to be limited to NASA affiliates, and especially involving the international science community? Because I know you mentioned the security concerns.
Yeah, so like I said, one of our guiding principles here is accessibility to the sample. So even for competed investigations inside the SRF, those would need to be open to the international, science community. The MSPG2 sterilization sensitive study identified a number of instruments and investigations that they think would need to be present inside the SRF, and we expect most of the opportunities to do those to be competed. But they did identify some things that aren't time sensitive and perhaps aren't necessary for the sample safety assessment, and so we can kind of hope that we get unsterilized samples out later. But if we don't, you can see this kind of red box on the lower right-hand corner where we would need to add contingency capability. So that may not be inside the original SRF. It may be a new modular building that can add additional capabilities if we find more things. But yeah, I do expect that all of those kind of science investigation opportunities would be open, to our international, partners, and would go through a competition process that's fair. Yeah.
Thank you.
Yeah.
Hey, Brandy. Andrew Gangadine, Cranbrook Institute of Science. First of all, that was very well communicated, so thank you. I'm wondering, so when these are being sent out or considered for analyses, there's seemingly an infinite number of analyses you can do on these samples, but some of them might be prohibitive of future analyses. So for instance, if you made thin sections of the samples, great, but then if you send it off to someone to do Raman spectroscopy, it might make a little divot in the sample that prevents, effective SIMS analyses next. So is there a, planned list of desired analytical order for these samples that's being developed?
Yeah, and that's a little bit of part of the sample, workflow planning. But I think one of the other things that, might be really beneficial is, when the proposals are being written to do these analyses, particularly for things where samples would be sent out, is for consortia, studies that propose a sequence of analyses that could be done on one sample to kind of maximize the use on this sample. I mean, as you may or may not know, once a sample is kind of released from, the custody of curation, you don't really know what happened to it or what kind of contamination it went through. So it's always going to be considered, obviously a non-pristine, kind of less, anything you find in that sample subsequently, you're probably going to assume is some kind of contamination because you haven't been watching that sample the entire time. So yeah, I think in terms of maximizing sample mass, you want to look at, sequencing the things so that you start with the least destructive analyses and then you progress to more and more destructive. Yeah.
This is back to the question about the headspace, gas in the headspace. It might be worth to have a procedure when you remove it prior to sterilization of the sample, because if there is like CO2 in that tube with the sample and you blast it with gamma, the rate of degradation can increase significantly. So if you
Yes, yeah,
that's
so,
that thought process.
yeah,
I'm sure you thought about it.
yeah, the notional workflow is that you would puncture the, well, and again, this is very preliminary stuff, right? But that you would hook the sample tube up to some kind of gas manifold to puncture the tube and extract the headspace gas before you extract the solid sample. And then you would hold that gas. And then you could do things that are sterilization sensitive on that gas, potentially even then sterilize subsamples of gas to go to, stable isotope laboratories and things like that. But you would definitely want to open the sample tubes and extract that gas before you sterilize the samples, yeah.
Hi there, I'm Tristan Caro from CU Boulder. These are really exciting developments, and I'm excited for the publications that are coming down the road. I'm curious, though, if you could elaborate on the sort of quantitative thresholding that you're thinking of using for the whole flow chart that you showed, and specifically, like, what sort of biomarkers are being considered for, like, that sort of, I think you used Bayesian thresholding, or you mentioned that a little bit.
You mean for the sample safety assessment?
Exactly.
Yeah, I'm gonna defer that question until the report comes out. But I will say that, and I believe that there is a notional number here on this chart. So this is, for example, 1 × 10⁻⁶. So this is kind of the number that the flight missions have been using. Is they want to assure that they have less than a 1 in a million chance of releasing a single unsterilized Martian particle into the Martian biosphere. So I think that's like a reasonable kind of starting point, is you want to make sure it's, less than a 1 in a million chance. But again, and feel free to follow up with me about that, and I can send you the report once it's finalized. We had a little publishing snafu that's held it up, but we do expect the paper to be available in the next week or so.
Great, thank you.
Yeah.
Yeah, thank you for your talk. This made it really put everything all in one place, which I find helpful. I'm Donnie Glazer from ASU. I had a question about adsorbed or mineral-hosted water, if that was going to be a part of the gas phase analysis in the workflow, or do we have plans for that?
Yes, I would say that the answer to that is yes. So we have a kind of, and again, I'll point you to the MSPG2 reports, both the sterilization sensitive report and the time sensitive report. And if anybody actually needs me to point them more directly to those papers, you could please come see me afterwards, and I can do that. Where there is a list of, potential things you would want to measure both in the gas and in the solid samples. Of course, the specific methods to do those measurements and stuff are still to be defined, but yes. Yeah.
Awesome, thank you.
Hi there, Haley Littrell from University of Arkansas. I was just wondering, after you've analyzed the samples for carbon-based life forms, do you have a strategy for analyzing those samples for non-carbon-based life forms, and what is the protocol for that?
Yeah, again, I'm gonna point you to the report, and actually, I'm not actually a co-author on this one, so I'm gonna point you to the report. But there is a section where you can see. So basically, everything that's based on carbon and life as we know it is up to this step 7. But then there is a step 8 here, and there's a little bit more information in the sample safety assessment framework report once it comes out about how they envision looking for life that's not as we know it, basically more agnostic life detection techniques. Yeah.
Thank you.
All right. Is there anything else online? Okay. Well, I guess. Unless there's any other questions, can all go eat lunch now.